All right, so this is going to be the second half of the weak acid strong base titration curve. So we've already figured out the equivalence point. We have determined which volumes we're going to find the pH for, and then we have done the first 4 calculations. So at the starting point before the titration begins, and 3 in the buffer region. So we have one last point to find the pH for before we can graph, and that's going to be the pH at the equivalence point. So if we remember, moles of acid equal moles of base, that's the purpose of any titration at the equivalence point, right? So that we can use the value of one known to determine an unknown. And so we determined at the beginning that it takes 30 mils of the 0.2 molar KOH to titrate against the 60 mils of 0.1 molar propanoic acid. And we've just shorthanded this to the generic version of HA. And I've already pre-written out the equation here. So you have HA being titrated with the OH. Because it's a strong base, the reaction only goes one way. And that's going to generate the conjugate base and water. So this would be the propanoate ion. In organic chemistry, when you have a conjugate, it ends in ate. All right, so we started out with this here. And if you multiply these two together, you'll get 0.006 moles. And again, at the equivalence point, these both, neither one should be a limiting reagent. They both should have the exact same values. So what you're left over with is 0.006 moles of your conjugate base. And we know that that conjugate base is going to set up its own dissociation. And so since it's a conjugate base, we know we have to add water to that, and it will regenerate a teeny tiny bit of the acid. Remember, most of it's going to stay in the A- form, and it will also generate OH-, which will make it slightly basic. So we're starting with 0.006 moles of A-. And we know that we're going to, because this is a weak base, it's a conjugate base, we know that we're going to have to plug this into a Kb value. Because if it's a base, you have to use a Kb. And again, let's rewrite the dissociation up here really quickly so we can remember what we need to find. Okay, so it's a Kb because that's an OH. So in order to find this Kb, because it's not on our Kb table, we're going to have to use the Kw. So you do this for any conjugate over the Ka, and we know that Kw is 1 times 10 to the negative 14, and our Ka was 1.3 times 10 to the negative 5. We used that previously in our problem. So we're going to calculate that. Okay, and you end up getting 6.69 times 10 to the negative 10. We also know that our Kb expression is going to be HA. It has to have OH-, right? Products over reactants over the A-. We always leave out the water. Okay, and so in order to figure out the values that we're going to need to plug this in, we're going to make a really quick ice chart, and we're going to keep this really simple here. So just, and again, I know some of you guys can skip this step. A-, HA, OH-, ICE. Okay, so this initially is, okay, so here's where our problem is. What is our initial molarity? We know that we have this many moles of it, but these typified charts we can't plug in for moles. We need to know molarity. And so what we're going to need to do is we're going to need to, we're going to need to actually change these moles into molarity. We know that molarity equals moles over liters. Well, we know the moles. And now we're going to need to find the liters. So if we go back to where we titrated, we had 60 milliliters to start with. We added in 30 mils. So we know we have 90 milliliters, and that's going to be 0.09 liters. So we take this and we divide by 0.09, and that's going to give us our molarity value. So 0.006 divided by 0.09 gives us a molarity of 0.067. So this is the value that we will put in for right here. So we have point, I'll have to write this really small. Okay, these would be 0. This is going to be minus x, like every other ish chart we filled in for these. This is going to approximate to the 0.067, x and x. And we'll take these values, we always take them, we're going to plug them in up here. So that step right there is where a lot of people get confused and mess up. All right, so just make sure you don't plug that in moles, because you're going to end up getting a very small number, and that's going to throw everything else off. So we've got our KB, going to be x squared over 0.067, and we know our KB value, we solved for that earlier, is right here, and now we'll just put it in the calculator and solve. All right, so since this is the KB value, we're going to solve for the concentration of OH, we solve for X, and we get this value here, and we take the negative log, that'll give us POH, and we subtract from 14 to get 8.85. We know it has to be above 7 because we have a conjugate base. Now what we need to do is go through and collect all of our pH values. So we have to go all the way back to right here. So we've got 2.94, and we're going to take this and we're going to plug this in, and our last step is going to be to graph the points and then complete the graph. So we have here a graph, and okay, so we're going to start at volume is equal to 0, so that's going to be right here. And I pre-made and measured out the graph, and so it's going to be 2.94, so we're going to make it as, oops, this is kind of hard to draw in here. Okay, so that's going to be our first point, okay, at volume equals 0. Our next points are going to be in the buffer region. So we have pH 10, we're also going to have pH 15, and we're going to have pH equals 20. So we'll look up those values and we'll plot them. All right, so I just went through and I went back. I found the pH when we calculated the buffer region for 10, 15, and 20. And I also found the pH, and again, these were all from our calculations, at 30, which was the equivalence point, which was around 8.8, 8.9. All right, so before we can figure out the pH, so if we can actually figure out the entire graph, we need to know the maximum value for the pH of just the base, because once we get past 30 mils in the titration, everything past this is going to be excess OH. And if we have excess OH, that's really going to dictate what our pH is. So in order to figure out that maximum value past a couple mils past the 30, is just going to be to take the negative log of the 0.2 molar. And when you do that, you get a POH of 0.69, and we subtract from 14, and we get that the maximum pH is going to be around 13.3. So that's going to be like somewhere, let's see here. I'll kind of do that in gray just so it's not going to distract us too much. So somewhere a little bit lower than that. Okay, so that gray line is representing the 13.3, 13.2, somewhere in that range pH. All right, so now what we're going to do is we're going to go through and we're going to draw our line. So let's see here, we got a nice pretty purple. All right, so we know initially there's going to be a pretty big spike, not a pretty big, I mean just compared to where the buffer region is. And then it's really going to level off. And it's going to stay pretty level until a mil or two before it reaches the equivalence point. And then it is going to jump. And then it is going to flatten out and start approaching. So it's an asymptote. So it'll start approaching that 13.3 but never reach it. So let's go through and let's label the regions that we have. All right, so we're going to go through and label each of the regions. So right here you have the start, and where we have the start, you're going to have primarily HA. Okay, so that's most of what you're going to have. If you drew a beaker diagram for this, you would have a teeny tiny bit of the A minus and a teeny tiny bit of H plus, but mostly what you have is HA. Between here and here, you're going to have the buffer region. And in the buffer region, you're going to have not exactly equal, but you're going to have similar amounts of HA and A minus. That's what makes it a buffer. And it's very important within this region that you star the halfway to the equivalence point. That's the 15 mils. Because here's where the pH, so if we read it from this point, our pH is going to equal our pKa. So if we take the value that's here, that will give us the pKa value. And then from there you can find the Ka. All right, so if we come over here, this is going to be our equivalence point. Very important to know that. And at the equivalence point, you have mostly A minus. And then everything up above here is just mostly going to be excess OH minus. And that's your titration curve. Again, it's very important to know what you have, what species you have in solution at all of these places, because that's frequently what they're going to ask you on multiple choice questions where you're interpreting the graph. That'll be very common questions that you have. Okay, I hope you enjoyed this podcast. Thank you.